Okay, in this problem, we've got another vector situation here, and I will let you pause it and read the problem if you're not familiar with this one, just to keep the video a little shorter. I'm going to get going. All right, so the programmed direction velocity given as p, vector p up here, which I'm going to use blue, is going to be in component form. This is going to be the same as 4, 7 if I take it out of the linear combination of standard unit vectors 4i plus 7j. And then A, which I'll use green, vector A, as the actual vector due to the wind, and I could call it the resultant vector. The reason I like the phrase or the term resultant vector is because if you look at the drawing down here, and I'm going to color code these two while I'm at it. There we go. And let's see. All right, so if you take a look at the two vectors and you read through the situation, basically the little quadcopter is programmed to fly in the speed and direction of the blue vector, but it ends up flying the speed and direction of the green vector because of the wind. So if you think about it, the wind, I'm going to use red for the wind, is really the difference here. What moves the quadcopter from the blue to the, and that didn't snap, so let me try that again, to the green here is that little red vector. So the component form of that may elude us, but this does look like really nice coordinates. You could maybe say it's 2 to the left and 1 up. But let me be a little bit more direct or mathematical about this here. I'm just going to use x and y for now. And check it out. If we set up an equation that says, hey, here was our flight program, and then wind was added to this situation. Okay. And the resultant vector, the actual vector that occurred, is A. So if we inject our component forms for these vectors, 4, 7 plus, we'll just say xy, and that has to all equal 2, 8. So it gets as basic as thinking of it as 4 plus what equals 2. Well, you could surmise real quick that the x value for w is going to have to be -2, which, like I said earlier, is kind of like saying, hey, it's left 2 and up 1, the little components there. And then if you focus on 7 plus the y value has to equal 8, so that as well is easy to figure out. That's just +1, and that's that up 1. Okay. So the question here is asking, what is the speed of the wind? So what if we know the component form? We have to now find the magnitude of that component form. So we're really looking for the magnitude of -2, 1. So that's going to be that little Pythagorean approach we're used to using to find magnitude is basically the square root of the sum of the squares of the components. So you've seen this many times, so I won't go too deep into the explanation, but we get radical 5. So nearest tenth, I'm going to double check this, it should be like 2.1 or something. Oh, no, 2.2. So the speed of the wind is 2.2 meters per second. All right, now the last part. In what direction is the wind blowing? Assume 0 is the rightward direction. And that's great because that means we're basically trying to figure out the direction of that red vector. Now, oftentimes we kind of put everything like A and P relative to the origin. So you might be visualizing it like that at first, but really what we should be doing is thinking of our little red vector in this situation. So take your, let me see if I can grab a copy of that. All right. And place that at the origin. Okay, so what we're really doing is trying to find the direction angle there. Like, what is the direction of the wind if a straight easterly blowing wind was 0 degrees? That's straight east. This is blowing more west and a little bit north. Okay, so I'm gonna zoom that drawing up a little bit because it's hard to see. So we could talk about that. But in the second quadrant, if you've got this, -2 and then up 1 situation here, what we're going to be trying to figure out is this, like I said, this theta over here. But this shadow or reference angle inside is really easy to figure out at first. We have a formula for this. Theta is equal to the tan inverse of the y value divided by the x value. The problem with tan inverse and popping that into your calculator is it's either going to give you a positive angle in the first quadrant or a negative angle from the fourth quadrant. And neither of those quadrants house our desired angle. We're looking for a quadrant 2 angle. So follow me on this. Let's put in our x and y value. That's going to be +1 over -2. And off screen, I'm going to do that here, making sure I'm in degree form or degree mode on my calculator. I get tan inverse -1/2. So -26 and we're going out to the nearest degree here. So -26.6 is what I get at first. I'll round it off when we're done. Now, let it be known that that is really a fourth quadrant angle. Negative angles drop down from 0. So -26.6 is somewhere in the fourth quadrant. The good news is that in order to find the angle we need, all we need to do is add 180 to that, and we'll get that desired theta I was mentioning earlier. So the difference between quadrant 4 and quadrant 2 is 180 degrees. Okay, so our tan formula did work. It just kind of gave us the wrong version of our answer. We need the second quadrant version. And so we do a quick 180 plus -26.6. And we get 153.4. I'm going to go back to red here. So red should be 180 plus -26.6. So the direction angle we're looking for is 153.4. So we'll round that off to the nearest degree, call that 153 degrees. All right, now that is the angle that's pushing us from the blue vector to the green vector at a speed of 2.2 meters per second. All right, I hope that helped.